Hello everyone, again we are back in our lecture class of energy conservation and waste heat recovery. If you recall, we were discussing thermodynamic principles which are very essential for the design of waste heat recovery system, and particularly we have completed the discussion on first law. We have introduced second law of thermodynamics and also defined the property which is of unique importance, entropy. And then in the last class I have also shown you how to calculate the change in entropy during a process when we are considering the change of state of a solid or a liquid or change of state of an ideal gas. For other cases which are also important, I think one should refer a book of thermodynamics, because we cannot go into much details, then we have to compromise with what we want to do in waste heat recovery. Well, so the basic equation of entropy or basic definition of entropy which I have given, and let me write it once again. ds is equal to dq by t reversible, and from there we get ds should be greater than equal to dq by t if we consider any kind of process both reversible and irreversible. Then by integrating one can write S2 minus S1 is equal to 1 to 2 dq by t plus S gen or delta S gen, because this is an integration process. So, this equation I like you to give some attention. This is a very important equation. This is change of entropy for a closed system during change of state from 1 to 2. So, you see what we have written here, S2 minus S1, entropy being a property of the system, it is a point function. S2 is the value of the entropy at the end of the process, that is at state 2. S1 is the value of the entropy at the beginning of the process, and then this change is given by the integration of dq by t from 1 to 2. We have to remember this will be dependent on the path, and then there is S gen, because if the process is not a reversible one, if it is irreversible process, then there is some amount of entropy generation. So, this is one concept, again very unique, and we should pay due attention to this concept, that whenever there is a process, there will be entropy generation if there is any irreversibility. So, entropy generation S gen, again one can write it as I have told, it is an integration process, one can write it delta S gen, or more correctly one can write it S gen 1 to 2. During process 1 to 2, whatever generation of entropy is there, that is your S gen, and from this one can easily appreciate, because this concept is familiar to us, this is a path function, it depends on the path. From 1 to 2, if the process has taken a path fully reversible, then S gen will be 0. If it has taken some sort of a path where there is irreversibility is there, we will get a specific value of S gen. If it has selected another path with different kind of irreversibility, then we will get another value of S gen. So, this is a very important equation, and this equation is called entropy balance equation for a closed system. So, this is very important. So, for a closed system, what we can see, that change in entropy, that is on the left hand side, that is equal to, or that comes from that generates, or sorry, that comes from the change of entropy of the system that results from heat transfer process, and that results from the irreversibility which generates entropy. One thing again I like to stress upon, I have shown dq by t, integration dq by t from 1 to 2. It indicates that there is only one heat transfer, but it is not so. There could be heat transfer from different parts of the system at different temperature. So, when we will proceed, it will be clear to us. With this, let us go to some next. What we can do, we can write entropy balance equation for an open system, or control volume. For an open system or control volume. So, how should we do it? You see, the concept of entropy balance can be done like this: S in minus S out plus S gen, that is equal to delta S of the system. Let us say during a process, during a time, let us say it is open system or control volume. So, we can understand it during a particular time. So, during that particular time, S n amount of entropy has entered the control volume, S out amount of entropy has gone out of the control volume, S gen, that is the amount of entropy generated within the control volume. So, summation of all these, that will give the accumulation of entropy within the system, or change of entropy for the system during this period. So, in terms of time, if I divide it, divide both the sides by some delta t, where delta t denotes the duration. So, one can write S in, this is rate, S out plus S gen, that is equal to d S dt, or delta S delta t, we can write it control volume C V. So, this is basically the top one I have written system, which is nothing but which we can write for an open system and also for a closed system, but now we are considering for a control volume. So, let us write C V. So, how entropy can enter this system? If it is a closed system, then there is only one way of entering the system, that is through heat transfer. But if it is an open system, then there could be heat transfer, and also through mass entropy can come in. So, for S in, what we can write? q k by T k plus sigma m I s I minus sigma m E s E, that is equal to, and plus S gen. This should be capital S gen, that is equal to S 2 minus S 1 of control volume. Let me explain what I have written. Q k by T k. To understand this thing, let us think of a control volume like this. So, I have schematically drawn a control volume, which notionally having 2 inlet and 2 outlets, to indicate that there could be multiple number of inlets and multiple number of outlet. So, this is some sort of a multi-port control volume. There are many examples in industry, and there are many examples from the domain of waste heat recovery. Let us say we are considering some sort of heat exchanger. So, heat exchanger will have 2 inlets and 2 outlets. Okay. So, this is a multi-port control volume. Mass is entering at through different entry ports, mass is leaving through different exit port, and there is heat transfer at different points. So, here heat transfer is at a temperature T 1. So, this is Q 1. Here heat transfer is at a temperature T 2, and the amount of heat transfer is Q 2, and here general some sort of a general mode of heat transfer has been shown, temperature is T I and heat transfer is Q I. So, summing all these things, all the heat transfer Q k by T k, that I will get what is the entropy transfer due to heat transfer. For a certain duration, again for certain duration, if Q k is the heat transfer for a temperature T k, then Q k by T k is the entropy exchange between the control volume and the surrounding, and the direction of exchange that will be decided by the direction of heat transfer. So, this is one part of input. Another part of input, there are number of input port. Through the input port, mass is entering. Entropy is an extensive property, it is associated with mass. So, entropy is also entering. So, m I s I, if that is the total amount of m I is the total amount of mass entering through a particular port, S I is the specific entropy of the mass entering through that port. So, m I s I will give me the entropy that is entering into the control volume through that port. Summation will give through all the port how much entropy has entered. Similarly, we can get m E s E. S gen is the amount of entropy generated during this period. S 2 is the S 2 I have written capital. So, it is taking care of the mass also. So, S 2 is the total amount of entropy at the end of our duration, and S 1 is the entropy at the beginning. So, this is what I can write, and dividing by time I can get some sort of rate equation, and the rate equation what I can have is this sigma q dot k T k plus sigma m dot I S I minus sigma m dot E S E plus S gen, this is also rate, that is equal to d s dt control volume. Okay. So, this is our entropy balance equation for an open system. Very useful in engineering practice and also for waste heat recovery. Here, let me point out a few things. I like to bring the diagram of the multiport control volume, which I have drawn sometimes back. So, here you see these are basically inlet mass flow rate, these are outlet mass flow rate, these are different heat interaction, this is work interaction. In our entropy balance equation, all the things which I have drawn, that has been put here, which are relevant, but you can see that there is no contribution of the work transfer term. So, this is important, this you have to also keep in mind, that due to transfer of work, there is no change on the entropy. Okay. Its implication we will understand later on. Another point I like to stress upon, that is the entropy generation. So, entropy generation, as I have discussed earlier, that it is related to the irreversibility of the process. So, if we can calculate entropy generation, so we should have some idea regarding the reversibility. During the process we incur the reversibility, that we will be able to calculate with the help of S dot gen term. And then this is one way of knowing how good is the process, how good is the transfer process. For an equipment, if we do this, we can have some idea regarding the design of the equipment, either for the design of the equipment or for the design of the process. S dot gen or S gen, that is very important term, and there are ways of calculating it. Even for waste heat recovery, if we want to analyze a system, this term is very useful. Let us take up a problem, and with the problem let us try to understand how we can utilize S gen, the concept of S gen, and know whether a typical process for waste heat recovery is good or not so good. Let us take an example. Let us say we have got a typical process. So, of manufacturing a product. So, a typical process of manufacturing a product has a number of sub processes. So, let us say the process 1 process 1 heating. So, we have to heat an object, okay. And then process 2, after heating, let us say we will have some sort of a goal, that means we can achieve some material property. Heating could be a part of the manufacturing process, but after that process is over, process 2, this is cooling, and once this is cooled, so it goes to process 3, this is finishing. So, let us say some metal object we are manufacturing. In the first process we are heating it, maybe to achieve certain material property or shape or whatever it may be. Then we have to cool it, because during finishing a process we cannot allow the hot object. Okay. So, let us say this is what we want to do, and let us take a very typical example. Let us say a 50 kg of iron block product. Let us say the product, what is the product? This is 50 kg of iron block, and this is during the process of heating, it is heated at 500 Kelvin, okay. And then it has to be cooled, to 285 Kelvin. So, now our focus is on the cooling process. Just to explain the entire thing, how it fits in, how it may fit in industry, I have described all these things, but our focus is on the cooling process. So, let us say in the existing plant, the cooling is done by throwing this piece of iron in a large tank. That is how the cooling is done, and then the tank is so large that we can assume that the tank is filled up with water, and the tank temperature does not change while the iron gets cooled, but the tank temperature does not change. Now, what we have to determine here, that what is the change of entropy of the iron block, what is the change of entropy of the water in the tank, and what is entropy generation. So, this is what we have to find out. So, let us do delta S iron, change of entropy of iron, change of entropy of water. We have to know it, and entropy generation. So, this is our problem statement, and then we will see what is its implication in waste heat recovery. All right. So, first let us try to find out delta S iron, that is equal to, how we can find out? Already in my last class I have discussed and I have told how to calculate the change of entropy for a solid body. Okay. So, it will be something like this. It will be m into, m is the mass, m into S2 minus S1, that is C average ln T2 by T1, and C average for iron, C average for iron is 0.45 kilojoule per kg Kelvin. Kg Kelvin. So, from there what we get, this is 50 into 0.45 into ln of 285 by 500. So, this will be equal to 12 minus 12.65 kilojoule per. This will be kilojoule, sorry, it will be not kilojoule per kg, it will be in kilojoule. Already we have taken the mass into consideration. So, this will be kilojoule only. So, let me write it minus 12.65 kilojoule. So, what is the heat transfer? So, this is the entropy change for the iron, kilojoule per Kelvin. This is the entropy change for iron. Now, what is the heat transfer? Heat transfer from the block. So, that will be minus Q out, that will be m into C average T1 minus T2, and putting all these things you will get 4838 kilojoule. So, this is the magnitude for iron block, it will be a negative quantity, and this will be a positive quantity for the water in the tank. So, now very quickly if I calculate what is the delta S for water. So, we will have 4838 by 285, that is 16.97 kilojoule per Kelvin. So, these are the values we will get from the entropy change of water. So, mind it, heat is transferred to the water, and that is why it is positive, and entropy change of the water, that will be also positive. That means, the entropy of the water will increase. So, we are not yet finished, some part is left, some implications are left. So, we will start from here in our next class.